Short introduction. Welcome for this Protect webinar, where the focus today is on vertical land motion, which is not exactly a big focus in Protect, maybe a mistake, and we will know more. We know that it's an important component for some location, and there are also some new measurements that are emerging, and we will know more in the coming hour. I don't remember in which order you organized, but thank you, Remy. Thank you, Robert, for agreeing, making this webinar, and the floor is yours. We are listening to you. Thanks.
Okay, I think I'm going for the first 20 minutes, and then Remy is going to go afterwards. I think then we have a discussion. Oops, gone too fast there. Let's try. Oops, and that's a good start here. Where did we end up there? Right. So we're talking about coastal subsidence and vertical land motion science to support climate change risk assessment. And what I want to do is really set the scene why this is important, and then talk about an activity that's being conducted jointly by Protect and Coquelicot, another European project on coastal climate services, that is trying to sort of draw a review together to think how we can do better in this space over the coming years up to AR7. So just a sort of bit of background, really, from my sort of perspective, this is an issue I've been interested in for a long time, probably for about 30 years. I've always wondered about sinking cities because some of the changes in certain cities are very dramatic, and we sort of did this work in 2021 looking at a sort of global analysis of subsidence and looking at relative sea level rise at a global scale. This work in China, which kind of repeated the exercise, but with much better data for China. We had this activity which Protect and Coquelicot was sponsoring, a coastal subsidence workshop last May 2023 in Paris, which we're still working on. You'll hear some of the results of that today. And very recently, in science, just sort of not specifically coastal, although there was a big coastal theme looking at some of the subsidence in China's cities that's going on. In the work I'm going to talk about, I want to particularly acknowledge a lot of people have helped. You can sort of see various names up there already, but 4 people have really been sort of very strong on supporting this. And first of all, Gonorrhea, who co-organized the Coastal Subsidence Workshop with me. Mano Shiraz from Virginia Tech, who's a geodesist. Philip Minderhouw at Wageningen University in the Netherlands, and Giels Erkens from Deltaris and Utrecht University in the Netherlands. So that they've worked very hard on the review, and the work I'm going to present is being contributed to by them significantly. So what's the problem here? Well, it's really about relative sea level rise. And, when we look, in Protect, we're looking very much at the big ice sheets. And so we're looking at the global components of sea level rise, or some of the components that can produce very large changes. But when you get down to somebody on a shoreline, they care about relative sea level, so you have to translate that global change and bring in the regional components, the local components, and also think about extremes when you're really going to understand what this means to people. And so the vertical land motion component and subsidence component then becomes quite important, because particularly if the land is sinking, you're going to have higher relative sea level rise than the sort of climate-induced calculations would suggest. And while vertical land motion comprises uplift and subsidence, so clearly we have both going on, there's a stronger interest in subsidence, as I think 2 reasons. It reinforces relative sea level rise. I've already said that. But also human beings exacerbate substance, and they don't really exacerbate uplift. So there's an asymmetry in the process in that human influences, which we'll talk about a bit more in a moment, like groundwater extraction, cause the land to sink, coastal land to sink. They don't. There's no opposite process that causes uplift, and this is often inadvertent exacerbation of substance. People don't really realize that they're doing it. It's certainly historically. And when we think about substance, it's probably, we think about something like glacial isostatic adjustment. That's a sort of process operating in the mantle. So I mean, it's global in scale. Substance is something that's happening much nearer to the Earth's surface. And so this picture here is just kind of capturing the idea of shallow subsidence and deep subsidence, whether it's, in the sort of unconsolidated sediments at the surface, or it's in the deeper consolidated sediment. And when we're thinking about substance, actually there's many reasons that substance can occur. One of the problems with this issue is, I mean, in a way, nobody really has a good as with sea level, it's a very complex issue. No one person has a good overview of all the issues, and so it takes teams of people to understand and solve it. And I think, vertical land motion science in the domain of its effects on relative sea level is in the infancy compared to climate science in that space. This picture here kind of builds on what I just showed, and it's showing the drivers. Again, it's focusing on subsidence. Green colors up here, if you can see my mouse, are natural processes. Red are human-induced. So I made the point about the asymmetry of substance. Humans exacerbate subsidence. So you have natural loading that causes compaction of sediments, and therefore a decline in a loss in elevation, or earth crust mantle dynamics, so tectonics, faults and things like that. But then we have a whole host of processes here, which might be shallow or medium or deep, sort of like loadings. And this is particularly true when you're talking about sort of soft soils. So deltas are a place where you have large piles of sediment that have accumulated over the last 7,000 years between friends, and maybe the surface sediments near the surface are really very young, only hundreds or even less years old, and so when you put weight on those, they're still consolidating, they haven't compacted, and therefore you can cause the land, you cause consolidation. Drainage is also a really major cause of substance. Just actually taking water out of these shallow soils will cause quite significant consolidation. For example, New Orleans is sinking about 6 millimeters per year, and it varies a lot. I mean, that's an indicative number. It's a sort of average, and it's due to the drainage. Another process that takes water out is the pumping out of groundwater. So people often want to get good quality water, so they go into it's reliable, so groundwater. It's also clean, in terms of disease, etc., treatment. And so that is another way of really causing very effective consolidation, or hydrocarbons. So that's kind of giving you but there are many other processes that could cause substance, old coal mines and things like. So you could write a book just on the processes that cause loss of elevation. One of the places where this happens most dramatically are in coastal cities, subsiding coastal cities. So this map shows the cities with more than 1 million people in 2005, which are in situations, they're mainly built on deltas. So you can see there's 2 dots, Amsterdam and Rotterdam in the Netherlands, for example, or Alexandria, or Vancouver, or New Orleans, I've mentioned already. And they're all around the world, but you can see there's a huge number in Asia. in South, Southeast, and East Asia. And it's so many, you have to blow them up to get an insert, and so you can see what's going on. And when you look at these cities, this is the maximum observed substance during the 20th century. The numbers here are not projections. It's the maximum substance observed. So 2 meters in Tianjin, 4 meters in Tokyo. So these are big numbers. A loss of elevation, fundamentally due to the pumping of groundwater. That's the story here. Although, I mean, again, attribution of these processes is problematic. There may be more. There's probably more than one process going on causing substance in these cities. So it's maybe not all groundwater extraction, but maybe that's the bulk of the change. And to put it into context, there's a time series here which shows. So it goes back to 1910. Again, this is the maximum substance. It's harder to get information on the average substance. What you can see is the first city that started subsiding in this set was Tokyo, about 1920, and it went down. Over here it said 5 meters. Well, you know, if you look at it in detail, maybe 4.6. It's more than 4.5. So if you round it up to a meter, it's 5. And something happened here. We'll say a bit more about that in a moment. Osaka is very similar kind of picture. Jakarta, the poster child of substance in cities, is kind of just disappearing out of sight, the red line. And just to make the point that, well, what happened in Tokyo in the 1970s? Well, they pumped groundwater like crazy through most of the 20th century. There was World War II. You can see World War II quite clearly in both Tokyo and Osaka. There was less groundwater extraction in World War II. And then it continued again. And then they realized this place is sinking like crazy. 1 million people in Tokyo live below mean sea level because of this process. And they started to provide water from surface supplies elsewhere, and they banned groundwater extraction. So this is what I mean by substance control. You can very quickly stop substance if you stop removing the groundwater or stop drainage. But it's not elastic. The process is essentially irreversible. So you stabilize, or even have like in Osaka, maybe it still continues to subside, just much more slowly. So these are both founded on very small deltas. So to sort of put some numbers on that globally, in the 2021 paper, we just sort of looked at, well, you know, what's the global signal of relative sea level rise? And we brought in satellite observations of sea level change. So observations, GIA estimates from the model of Peltier, estimates a data compilation of delta substance in 117 deltas worldwide, and city substance, the additional substance beyond deltaic substance that's happening in these cities. And these 4 components are assumed to be independent and hence can simply be summed. And to give you the point that this is having a global signal, the red line is coastal relative sea level. So its median's about 2.5 millimeters per year based over this period. The blue line is a different take. It's population weighted coastal relative sea level. So the red is weighted on coastal length, not area, on coastal length. If we take a view of, well, we don't really care what the average piece of coast experiences. We care what the average person experiences. And we can see that 12.5% of the world's coast is meant to be sinking, according to this. It's meant to be rising. Sorry, it's above zero. So this is land that's rising under current conditions. Only less than 1 million people live there. So you have so it has very billion effect. So the whole curve is shifted about 2.5 millimeters to the right, and with a tail. And if you look at the numbers, 2.6 millimeters per year is the global mean sum. 8 to 10 millimeters per year is the coastal weighted population. So saying that people actually experience, I mean, relative subsidence really matters to the human experience of relative sea level in the world's coastal zones. And if you look at these plots, you can look at, just unpick, well, what's causing what? If you look at the top plot, length weighted, you can see climate, and then actually GIA is the blue. You add in GIA, it actually tends to reduce slightly the amount of relative sea level rise that's experienced. And you can't see the green and the black plots because they're affecting quite a small length of coast. If you go to the population weighted below, so you do the same calculations, but with population weighting, you can see that the curves actually, the green and black become rather prominent, and they separate at about 25%. So it's about 25%, about 75% of the world's population is living in subsiding deltaic cities. Essentially, what this is saying, which is about right, and so they're seeing a lot more relative sea level rise. So the Protect review, so which we wanted to sort of think, well, what can we do about this problem? And we'd also had the AR6 results for which made much more effort to understand vertical land motion. I'll say a bit more about that in a moment. But when we look at vertical land motion research, we find it's complex. I think we find it's fragmented and sometimes, maybe often, ignored. So we believe there are real important benefits of explicitly addressing vertical land motion, particularly human-induced subsidence. And our review is considering 3 questions within a holistic framework, I think, which hasn't existed in this space at all previously. It's been rather fragmented in the overall approach. What has happened historically? So we're interested in observations and their analysis. What amount of subsidence or uplift has happened? What might happen in the future? So we're talking about projections, and that inevitably means modeling. And thirdly, what kind of societal responses could actually are relevant to dealing with this problem in the context of climate change and sea level rise? And really, we're interested in how the IPCC has addressed subsidence, so that's a relative sea level rise to date, so we're looking at AR6, and how it could benefit from new research, observations, and modeling frameworks to deliver more actionable outcomes for people dealing with coastal adaptation. And let's look at observations first of all. So this is a plot that Amy put together, and it shows you the AR6 sea level estimates versus this is the VLM projections. It's the VLM component as estimated by the AR6. What was done was it was based on AR5 looked at GIA, so they took a sort of modeled estimate and applied it to the oceanic components. And in AR6, they looked at tide gauges and basically extracted a residual, which was assumed to be vertical land motion. And then this is compared here with GNSS, Global Navigation and Satellite System measurements. And what you see is that in places like North America, in the top left panel, there's pretty good agreement between what's coming out of the IPCC and the observations from the GNSS. And of course, there's a high density of observations in the GNS as well. And the same is true really in Northern Europe. You can sort of see the uplift in much of Scandinavia, to a lesser extent in Scotland. And then as you move down into sort of England and Northern France, you're getting more neutral or the land is sinking and you're getting sea level change. So I should say that red here means the land is sinking, blue means the land is rising. But when you go to places like the Mediterranean, then you find, well, there's a lot of gauges, there's a lot of tide gauges in the north, but there aren't many along the North African coast. And we know that, for example, the Nile Delta is sinking quite substantially in places around Suez, for example, 5 millimeters per year. and you're not seeing that at all because there's no tide gauge there. So it's not really so good. And then if we move to the last panel, there's one tide gauge in the Philippines, which is applied because of that reason to a very large region, and the GNSS shows a completely opposite trend, and they're not at the same location, so they're not inconsistent. What I think is showing is that the scale of substance can be quite local, and to extrapolate it over the scale that's been done here is not appropriate. So I think really the overall message here would be that the AR6 has probably would have been better off trying to find other data sources if they were available to sort of deal with areas like the Philippines, because you get these kinds of problems. And I suppose the GNSS, we have there was quite a lot of work on sea level in the GNSS, and there are multiple solutions as well. It's worth noting SONEL, which is I think specifically derived really to work on sea level science, but there's also the NGL-14, the Nevada solution as well, which uses more gauges. So it depends on the kind of question you're asking. The results and it's this contrast. I mean, they're not identical solutions when you bring in other data sets, but it sort of gives you a feel for the kinds of data that you can see. And just looking at Chesapeake Bay, you can see that's an area that's sinking in the top, or Stockholm on the right at the top is an area where there's uplift, sort of consistent with what we're seeing. And equally, some places are temporarily changing. So Mayotte down here in the bottom right-hand corner where my mouse is, stability, and then quite significant subsidence, not an abrupt subsidence, not an earthquake, and then stability. So you get some interesting sort of patterns. And so GNSS, though, we only have that data at a few points, but what we also have now is INSAR. So sort of radar-based satellite system which can measure reflectors in lots and lots of locations. And by putting these together, you can then calibrate the INSAR measurements to the GNSS and actually get geodetically meaningful results. And therefore kind of start to think about getting global data sets. So this is the vertical land motion service from Copernicus, which Remy's going to talk about in a minute, so I won't steal his thunder, but just to make the point that we can now start to have these very wide-ranging and rich data sets that show interesting patterns, as we sort of saw in Northern Europe in the earlier sorts of plots. So observations, we're making great progress, and INSAR and GNSS now give us the capacity to look at what's happening almost everywhere. And sorry, I'm probably talking a bit too long here, but for prediction, we have to sort of attribute that. Why is that happening? And we have to link it to a model. And if we look at the example subsiding cities, we can see straight away here, these are not uniform in time. If you extrapolated parts of these records, you get it completely wrong, particularly if you measured sea level at Tokyo, or level substance at Tokyo from 1920 to 1960, and you projected it to 2020, you would be completely wrong. So you need to really sort of be quite circumspect when you're thinking about projections. And so there's the issue of attribution. What's causing the substance? How will the drivers of substance evolve in the future? Will they be stationary, in which we can just extrapolate, or will they be nonlinear? And so this paper here by Philip Minderhout actually looks at the Mekong Delta, and actually for one place actually does come up with different scenarios of substance over the 21st century, as we're kind of familiar maybe with sea level rise. So this is work that's still sort of beginning, and other papers are sort of looking at this, but it's certainly something that's not as mature as as the observations. But there's huge potential here, and I think a lot of progress will be made. Thinking about responses to subsidence, if we look historically, the response has been to adapt. People have generally built walls. If you go to all those Asian cities that have subsided a lot, you'll find big dikes. If you go to the Netherlands, you'll find dikes as well. So that's a kind of a pretty kind of common response. And what we're doing here is and we're developing is trying to think about how things have been done within IPCC, protect, accommodate, and retreat, and thinking through the different types of responses to subsidence. We are also thinking through the idea of subsidence control, what they did in Tokyo. That has been done in a few places, but not as many as you'd think. And really, or engineered sedimentation. Maybe if there's a supply of sediment, maybe we can actually use that to build elevation. So this is work that we're sort of still thinking about. So and developing as part of the paper to get people to think about, and I suppose the point is many of the adaptations are identical to what you do to sea level rise, but things like subsidence control or is not. And so there are differences from thinking about how you respond to climate-induced sea level rise. So anyway, concluding remarks. So vertical land motion in the IPCC AR6 scenarios has low to medium confidence base because, and I think really the tie gauge network is insufficient in density and also the temporal aspects to really capture current vertical land motion. But we're lucky. The invadability of the INSAR and GNSS data is providing a revolution in vertical land motion observations, which can really benefit AR7. So I think we can have a transformation of information on what's happening today or what's happened over the last 20 years. I think when we think about going to the future, that's a bit harder. It presents challenges. You've got to think about why is the subsidence happening, and then developing models, and then when that involves people, you've got to have scenarios of how people will behave. But progress is expected. You know, it's something that people are doing. I think linking the vertical land motion observations and projections to adaptation responses and subsidence control will be fruitful as well. Thinking through the practicalities of responses and really and getting sort of joined up thinking about adaptation as well. I think targeting the IPCC, there is a special report on cities, and so we're talking a lot here about cities. So I think that's a hotspot for this issue, and AR7 will provide a focus and provides if like a customer for this kind of thinking. But just to remember, I mean, I said at the beginning, the VLM community is quite fragmented compared to the sea level community. And I think this hinders progress. But I think one of the points in the review is that lessons can be learned from the climate experience about how, thinking about more holistic frameworks, how people can work together and really develop understanding in this space and improve things significantly. So with that, I will conclude and I think hand over to Remy if I understand what's happening next. So I'll stop sharing.
Yeah, I think I continue. Thank you, Robert. And I share my screen now. So here. Is it fine? Now I put it in a presentation mode. Is it fine?
Perfect. Yeah, thanks.
Okay, so let's go. Thank you very much, Robert. And actually, I think you made pretty much very well the introduction for me. So I don't have to spend too much time in the introduction. And in any case, I'll try to keep it short. But so it's a study we did about the coastal subsidence in Europe. So within the framework of the GSU European project and Coquelicot project. So basically, the idea is to map subsidence or vertical land motion at the scale of Europe, but more precisely subsidence. And we took here about the coast because Coquelicot is basically mapping the coast at risk. So, as Robert said, like the land subsidence can be very, very sensitive locally. And so here on the right, for example, you have an example of Jakarta, that is a place where you have a strong subsidence, and basically the climate-related sea level is less important than the subsidence itself. That creates a lot of issues. So the problem with the subsidence is that it's very difficult to characterize because, as Robert said again, it's very sparse, the data in time. It can be sparse also in space, and very much in space actually, like the GNSS stations are irregularly placed, and they can provide really local information or global information, so it's difficult. So what we try to do in this work is to take the advantage of this new European ground motion service to start to help filling the gap of vertical land motion at the scale of Europe. So the EGMS product, sorry, I just moved something here. Okay, so the EGMS product is basically, you have a map here, an example of what it provides. So it's at the full scale of Europe. And so basically it takes the advantage of INSAR, so mapping the relative land motion compared to reflector in a rather small scale, like basically 50 kilometers, that they couple with the GNSS gridded model, which is based on 3,000 stations in Europe. So they can have basically vertical land motion that are expressed into international reference frame. So that is directly comparable with sea level. And so EGMS is designed to characterize land motions with millimeter precision, so which is very important because it's also used for example, landslides, but in landslide, the land motion are extremely strong. And for coastal subsidence, it can be quite tiny, but still important. So 1 millimeter precision is what basically we need to sort of characterize if subsidence is happening or not. We have 3 products, so L2, so it's really INSAR only and based on line of sight. So it's very something that is relative to a specific point. It can be very useful. L2B, which is INSAR 2, but calibrated to the GNSS gridded model. And L3. So L3 is no longer in line of sight. It's very, very vertical and horizontal that can be directly compared within international reference frame. So comparable with the sea level. And actually, this is the product we're going to use. And so basically what provides EGMS is estimates of vertical land motion with pixels of 100 meters per 100 meters, which are exactly the same pixels that are used for Korean land cover. 2 versions have been released yet. So here I'm going to use the first version because I downloaded the data and you'll see that it was pretty painful, but using this new EGMS service to identify coastal subsidence zone. So the data set is basically this EGMS release, but there is no API on this website, so you have to download each tile one by one. And actually, if you cover the full coastal of Europe, the full coast of Europe, you have to download 415 tiles, which are each 100 kilometers per 100 kilometers that then you merge together. And so we restrict the analysis only to coastal floodplains. So really with the risk of flooding. So the first thing we did is to compare these EGMS results with independent GNSS station data to see sort of to validate the vertical land motion of EGMS compared to independent measure of vertical land motion through GNSS. We use also a model, a GIA, to sort of understand how much of the subsidence is due to GIA compared to the rest, like for example local things. For the exposure, we took the Korean land cover, and to define the coastal floodplain, so basically we took the large Copernicus digital surface model that we coupled. So this was done by Daniel Linke, but the bathtub flooding for 1 in a 100-year event plus 2 meters sea level rise. So it's pretty a maximum extent of the problem. So where we have these coastal floodplains. So we end up with 41,000 coastal floodplains in Europe. And so the first action was really to compare this EGMS new results, like within the geocentric reference frame with the GNSS independent. So we took the GNSS actually from SONEL, so the University of La Rochelle, what Robert just showed before. So here on the right, basically, you have a coverage of coastal pixels of the EGMS. When it's red, again, it's like you have subsidence. When it's blue, you have rather an uplift. And so what you see here, basically, so here is the Atlantic coast of France, but it's extremely orange and red. So meaning that it seems like you have a strong subsidence by EGMS observed throughout this coast in France, which we know is not the case actually. So first we feel that there is a bit of a problem here, and the GNSS station are here the triangles in white. And so basically what we did is like we take the collocated EGMS pixel and we compare with the GNSS results. And here you have like it sort of is a good agreement, like the correlation is pretty high, which is good, but you have a bias. And so basically what we found is the EGMS tends to overestimate the subsidence that you actually have. And you have a negative bias of roughly 1 millimeter per year. So it means that EGMS, if you do the data, will have more subsidence than you will get from independent GNSS results. So we investigate that a bit more to understand where does that come from. And so basically, EGMS is calibrated from GNSS stations that are expressed within the European Geodetic Reference Frame, ETRF 2000, which is an old one, which was like more than defined 24 years ago, and really focused on Europe. And exactly the how to say that? Maybe by law in Europe, when we design something, we have to use that European Geodetic Reference Frame. But what we know is like we have new geodetic reference frames that are more accurate, and especially the one from ITRF 2014, which is used by GNSS teams like NGL and ULR. And if we compare the stations that were used in EGMS, whether they are expressed in ITRF 2014 or ETRF 2000, you see the difference here, and you really see that you have when you use ETRF 2000, you have too much subsidence compared to when you express within the ITRF 2014. And this gradient actually increases when you go northward in Europe. So basically what we found, so we could define a very simple function to pass from ETRF 2000 to ITRF 2014. So we could express all EGMS data from that ETRF 2000 to back to ITRF 2014. And what shows that that analysis is really we have an overestimate in the EGMS of the subsidence, but it's only due to geodetic reasons and can be corrected quite easily. So now we have a function to correct our data. We can now start to make the analysis in coastal floodplain. So here you have an example of the coastal floodplain in Arcachon, which is here, the green square. So here you have an example where you have like these coastal, each colors here, each lines define the coastal floodplains. If they are black, it's because they have a lot of pixels. If they're gray, it's because the pixels coverage is not so high. And so what we can do is like we can make statistics within these coastal floodplains. So here, for example, I'm going to show the average, but you can average within the coastal floodplains the vertical motion of all pixels. And then, of course, this is a strong subsidence, but once you're corrected from ETRF 2000 to ITRF 2014, then you see that you have still subsidence, but it's less strong, less pronounced, but still you have subsidence. Okay, so now we have a way to correct and a method to calculate the subsidence within these coastal floodplains. We can also calculate for each coastal floodplain the distribution of the pixels. So here you have an example. It's an example of a very large one, which is located in Italy. And so what you see is basically the mean is more or less representative of what happens is like basically when 80% of coastal floodplains with an average subsidence stronger than 1 millimeter per year are covered by 75% of pixels with a subsidence that is stronger than 0.5 millimeter per year. So basically, if you have a mean subsidence, it means that overall it's subsiding. But we'll see that there is heterogeneous situation within coastal floodplains. So the first thing we look at is really a full pan-European situation. So here it's expressed basically the mean vertical emission in coastal floodplains and counted by number of coastal floodplains. So I said there is 41,000 coastal floodplains. The gray bar is when you take the native EGMS data. The black bar is when you correct from for the geodetic reference frame, and the residual is when you remove the GIA to the black one. And so what we see is a very large number of coastal floodplains in Europe are actually in a uplifting situation, and quite a few actually, and especially less if they are corrected, are subsiding. But this is per number of coastal floodplains. So now if we look at, if we weight by the average of the area, of the coastal floodplain, then we end up with something that is very different. And what you see here is like 50% of the coastal floodplains in Europe are actually subsiding at more than 1 millimeter per year. And you have up to 10% that are subsiding at stronger rates than 2 millimeter per year. So which is quite substantive. And what you see here is like basically this very large number of coastal floodplains that are in an uplift situation are actually a very small area, which is basically corresponds to the coastal floodplains in Northern Europe, where the GIA is basically contributing to the uplift. So, and if we look at a national scale situation, we can really find this GIA here, which caused an uplift in the northern countries, coastal floodplains. Here, near Latvia, Lithuania, Denmark, and the UK, you have rather stable conditions. Also, we know that in some places you have subsidence, some places you have an uplift, especially in the north, for example, of UK, due to GIA still. But in Southern Europe, you have very countries that are really affected by a strong subsidence. And what we see is, like, for example, the Netherlands, Germany, but also Italy, where Italy you have a very strong subsidence, which is mainly due to the Po plain, the delta of the Po region. So now, so it really shows that with EGMS you can do a national scale, European scale assessments, but because it's 100 meters per 100 meters pixel, you can really make dedicated studies within a very you can zoom in some regions. So here I take 4 examples. The 2 first ones are examples where we know that subsidence can be strong. So the North Italia coastal floodplain, so basically the Po delta. You see on the right where you see a very strong subsidence, which is associated actually with Acqua Alta in Italy. But you see that you have a strong subsidence larger than in some places 5 millimeters per year, and it's quite homogeneous, basically the subsidence pattern here in this coastal floodplain. While in Netherlands, it's also known that you have a strong subsidence, but it's more heterogeneous because the process are different. You have a very strong contribution of gas extraction here in Groningen, so that's why you have a very strong subsidence. And in Rotterdam also you have, but it's not because of gas. And in between, also, you see that some spot of strong subsidence or medium subsidence, so it's quite heterogeneous, and actually EGMS can help really to look at these patterns in more details. But it's also very useful because, for example, what we found is like Thessaloniki Airport. You see an Axu Delta. You have a very strong subsidence, which is actually due. So it's in the Delta region, but also a reclaimed land here in the airport. So we can really characterize with EGMS. And what we also developed in this study is like we identified a new region with a very strong subsidence, which is located in the south of Italy. And actually there is a GNSS station nearby that shows also a strong subsidence, where you see here like more than subsiding at more than -5 millimeters per year in this region. And finally, what we did is like, so we focused on coastal floodplain, but what we can also do is compare directly with the land cover. So here I focused on 3 types of land cover: urban fabric, which is basically cities, harbour, and airports. And either no weights, or as Robert did before, weighted by either the area that is occupied or the population for the cities. And what you see basically, so this gives you the mean subsidence, weighted or not. Here it's all Europe in this table, and here it's only in Europe that is not affected by the GIA uplift. And what you see is like basically, which is I think the most important, is in population is on average leaving a 1 millimeter per year subsidence at the scale of Europe more than 0. So it's basically an enhancement of sea level rise. So if we have 3.5 millimeter per year currently, it will be more 4.5 that is actually experienced by the population in the coastal floodplains in Europe. And harbour is 1.5 millimeter per year enhancement of a relative sea level rise, and for airport is 1 millimeter per year. So basically, I come to my conclusion. So we have, with this study, we present the first pan-European contemporary coastal vertical land motion based on this new EGMS product. What we found is the urban zones as population that are in flood-prone area are experiencing a mean of 1 millimeter per year subsidence, if we exclude the Northern Europe that is uplifting due to GIA. In harbors, it's even more. And actually, harbors are critical infrastructure where the sea level really matters. So I think it's an important message. And also, I think having this EGMS is not the full story, because we have found that we can have biases for just geodetic reasons, and this really needs to be accounted for, especially if you look at small signals that matters, which is the case for sea level. So the paper should be soon, hopefully, published in Earth's Future. And so the next step are to use the new release to compare with the first release to see how we can, which type of, if our previous analysis is, for example, linear, robust in time, how to use also this is an open question, but as Robert said, like how can we use this information for projecting in the future, which is like we cannot just draw a linear extrapolation for 100 years. This wouldn't work. So we have to design some methods to do it properly. And also we plan to release this data set on the Coast platform. So with that, I thank you for your attention.
Thanks a lot, Robert. Thanks a lot, Remy. Are there some questions in the attendance? Please do not hesitate to raise your hand, or even we are not so many, jump in and ask your question. Okay, then shall I start? Remy, there will be a regular update, and at which rate we expect to see change? Because on the slopes, on the vertical subsidence for city and the example of Tokyo, we can see that it can be stopped pretty fast. I expect if people stop pumping. What is the rate of the update, and are we expecting to see big change in the behaviors? Might it help in the projections?
Yeah, I think
was the question.
For the behavior, I think it very much depends on which process is acting. Typically, some processes are very linear, so you can more or less like make a projection quite easily. But as I say, well, EGMS just take the whole thing, and then you have to decipher yourself to disaggregate the information to be able to make a projection. For example, I've seen an example in Nice, where actually vertical, and so Nice airport is sinking, and at a specific rate that can be really well modeled, which is because of reclaimed land and compaction of sediments. They can really make a modeling of that, and actually this is followed for 15 years. And I've seen a poster in EGU where they showed that very nicely. In EGMS, you adjust 5 years periods that are changed all the time, and I think every time they change a time period, they also change the number of stations in the calibration. So it's not necessarily easy to put all this data together, and at the end they only keep 5 years on the portal. So it requires more, I think. You always have access to previous version, so at the end you can have a very, very long time series, but you have to be very careful of the consistency of your time series, because the reference may not be exactly the same from one release to another. And I think they're releasing every 1 to 2 years a new product, which is always 5 years.
Okay. Anne, please.
Thanks a lot for your presentations, both. I was wondering, since it's so hard to make predictions or projections for the future, what do you tell stakeholders when you say, you know, that's the projection from the cryospheric component or the thermal expansion, but do you tell them to add something like that makes quite a big difference in some cases? And how do you tell them, and what do you tell them to add? How does it work?
Well, if I answer, I mean, I think we're still thinking this through, really, to be honest. I mean, in the 2021 paper, we did actually we did project for 30 years, just a linear extrapolation. That came across as a reasonably sensible timescale to assume linearity. Although it's still essentially a scenario. I mean, we are using those observations like a model, really. I think to go beyond 30 years with just simple extrapolation doesn't make sense. So then you really have to, you're moving into into some kind of modeling sort of framework. I think one of the questions actually is how far does it make sense to think about these changes? With sea level, with climate-induced sea level, we know that there's tremendous inertia and very long-term commitments. So it makes sense physically to actually look 100 years, 200, even 300 years into the future. Those are meaningful numbers that are robust to our assumptions about emissions. And I'm not so sure we can ever have that level of understanding with substance, because it's so much more complex. So I think maybe we're always going to be focusing on a shorter time window, and clearly people can, certainly with some types of subsidence, people can very quickly influence it, as Gail made the comment. So it's a slightly different problem. So anyway, that's a bit of a long answer. Hopefully it's helpful.
Thanks.
Michiel, please.
Thanks for the very interesting presentation. I was triggered by the time series of subsidence of the various cities around the world. And the fact that subsidence can be halted by stopping pumping up groundwater, apparently. Is there a theoretical possibility that it can also be reversed?
No, I mean, because basically speaking, when you get consolidation of sediments, these sediments are geologically young, the grains are not actually in contact. So when you remove the water, you actually allow the grains to move to grain contact, and it kind of goes to a maximum bulk density. So there, to take it back to the state it was before, you'd have to, push those grains apart. It's just, it's not really physically possible. There is, I think, you can think about, for Venice, people have thought about trying to pump water back in under pressure, and maybe you can get 20, 30 centimeters. So you might be able to get a little bit back. And I think in Tokyo, you actually did see a slight recovery, but it was much, much smaller than the loss. So I think you might get 20 or 30 centimeters. And if sea level isn't very fast, that could buy a bit of time. So I think that's as far as you can really take the reversibility of this process with our current understanding, unless there's some kind of major breakthrough. But I think, no one is talking about that. So I think that's science fiction at the moment.
Thanks. And I have a question for Remy. You showed this very nice map of subsidence in the Netherlands, but you did not explain, or I missed it, why there was subsidence around Rotterdam, which was so outspoken. Is this because of the newly claimed land in the Maasvlakte, or is it something else?
To be honest, I'm not fully sure. I didn't dig it further, but I think there is a bit of mass load on but also I think it was built the city on peat oxidation. You have an effect of peat oxidation that is still going on, and it's several factor. And you have also, I think, a bit of GIA, but this is small compared to the rest. So I think it's a mixture of peat oxidation plus loads of infrastructures. But it's quite significant. But I've seen also a cluster at EGU. It gets really problematic actually, because some buildings are really damaged because of the subsidence in this region. So it's really a problem that is not only about sea level, but also on the building infrastructure perspective directly. So can you live in the building or not anymore?
Yeah, thanks.
Other question? I have a last one. I don't know if anyone can answer. It's related to the projections. I can see pretty easily I can see how you can model the impact of putting a load on the surface, and that with sometimes it will change the ground and sink down. I don't see how you can anticipate that when it's related to a switch in pumping, for example, or in the behavior of the population. So what are actually the tools to predict the vertical land motion and the subsidence in these various regions?
Well,
Is
I'm not an expert.
models or social models or a mix of both?
I would not call myself an expert, but I think basically speaking, there are people like Nicholls, Erkmans they have hydrogeological models that allow them to look at basically the effects of water withdrawal and how that affects the density of the materials, and then you can translate that into a loss of elevation. So I think it's really those types of tools. And then so I think, so you have a physical component there, which is based on hydrogeology, but then the drivers of the model are also human behavior. in terms of then you have scenarios of how much water are we taking out. And one scenario is we stop taking water out and maybe let the water table recover. So so I think the hydrogeology, I think, is quite strong physically based sort of modeling. What the uncertainties do lie in the realm of human behavior. Will we adapt, and will we keep on adapting? I mean, the case of Venice is always interesting because Venice subsided quite a bit in the 20th century. Now that is not happening. But of course, so they're not extracting the ground, they're not mining the groundwater under Venice. But around the Mediterranean, with growing drought and water problems, you wonder whether the pressure to withdraw groundwater might regrow. So you understand. So you've got to keep on policing this forever, really. So there's a, but your assumption would be with Venice, I suppose it wouldn't start again. But I do wonder sometimes.
Thank you. Is there a last question in the audience? It seems not. So again, thanks a lot, Remy and Robert, for your talks. Very inspiring. And enjoy the rest of your afternoon all. And thank you for your time. And see you soon, sometimes, somewhere. Goodbye, all.
Thanks a lot. Bye-bye.
Bye. Thanks.
Bye, thanks.
Bye-bye.